Hello again. This video is going to be a walkthrough, a step-by-step description of the code that I'm providing for the tree project, the binary tree project in our class. I hope that will help you understand how the code works and help you see more clearly where you need to make adjustments to the code to complete the project. So let me share my screen. And a very brief presentation just to show you a couple of things about what classes are actually being used. Then we'll jump right into looking at the code. So this is kind of a walkthrough. You might get a walkthrough that might be the only training you get in some cases. You start a new job with a company and they have code they want you to work on, and somebody's worked on it before, but it's kind of incomplete. And your job as the new person on board is to finish it up. And the only training that you may get on this code, other than what you already know about coding from your classes and your work experience, is that whatever the explanation is that's provided to you in like a 10-minute overview. Well, here comes the 10-minute overview. The classes in this program, this is startreestarter.py. That's the version of the Python program for building a tree and displaying a tree that you're going to be working on. And one of the classes is called star. So that's just basically a container that holds the information for one star, one stellar object, read from this file with the horrible naming convention, HABHYG. There's actually several files I supply. I'll go into that in a little more detail later. I don't know what the HAB stands for. I think it's the initials of the person who compiled them. HYG stands for Huygens, which is a satellite program that developed a catalog of many stars as viewed from orbit, and that database is used extensively by astronomers. This is a very small subset of what's in that database. So that's what a star object is, star class. A tree node is basically one of those gray boxes you saw in the earlier presentation. This is the actual things, objects that get connected together via the links to form a tree. And so it is based on a star object. It contains a star object to contain all the data that we're loading from the file. And it adds left and right references, which enables the star to be inserted into the table without actually touching the star object itself. It's a very common pattern is that you have a data object embedded in some kind of node object. Then the node object carries the overhead that's required to actually collect the data objects up into some useful format. There's tree. A tree holds a binary tree structured collection of tree nodes. So this is essentially this is the tree. This is the thing you see in a diagram with the boxes and the arrows. It keeps a pointer, or reference actually, to the tree's root node, because you have to know where to start, and you'll see everything starts from the root. So one job that tree has on top of tree node is just to keep track of which tree node is the starting place. This also is the class, tree is the class, that contains the insert, pre-order print, and search methods that you will create and add to the starter code to complete the project. There's another class you'll see in there called trunk. It's purely a helper class used for the code that I borrowed from the internet, which actually draws the diagram of your tree after the tree is completely built. So we're not actually doing anything with it directly. But I'll point it out just for reference in case you see it and you wonder what it does. There's no inheritance in this program, and that's actually kind of common. I use object-oriented programming almost all the time for most of what I do. However, I don't use inheritance much. I haven't found that to be very useful. I find containment, where one object contains another, or one object is a collection of others, very useful. That's the real basis of data structures in most high-level languages. but actually having at least an elaborate inheritance hierarchy, I think, is largely an academic matter. I mean, it's appealing on an intellectual level, but it isn't really very useful because there aren't very many situations in the real world that fall into vehicle, and a car is a vehicle, and a truck is a vehicle, and a train is a vehicle. It just doesn't line up like that. Usually these are special purpose classes that you create to hold the data to solve the problem that you need. Those classes interact. The interaction between classes is critical. When one class uses another, that's important. When one class inherits from another, I think, personal opinion, not so important. Okay, so let's look at the code. I'll stop the presentation and I'll go over and pull up the actual code. This is in Replit, which I'm sure you're familiar with. You don't have to use Replit to complete this project. I've also got it running in Visual Studio Code, so it definitely will work. Nice thing about Python, it's pretty portable. It runs on my Mac, it runs on my Linux machine. Don't currently have any Windows machines, but I'm sure it will run on your Windows machine as well. So starting at the top, there are two imports on line 5 and 6, an import for CSV and an import for time. Time we had before in the previous program. That brings in the timing routines that you can use to see how long, usually in nanoseconds, particular operations on your data structure took. CSV is a class, is a module that brings in methods to read from a comma-separated value file. Now, you may be familiar with comma-separated value files from a couple of different contexts. They're very common as a file format, and Excel can read them and write them, among many other programs. They're very easy to use and relatively unsophisticated file format with values separated by commas, as the name implies. Python methods in the CSV know how to read those and process them and deal with the first row being a header of titles and all that kind of stuff. So this time, rather than using JSON, we're going to be using CSV. I think it's a lot simpler, actually, although JSON was kind of cool because it was such a functional, 1 or 2 lines of code were so functional. Okay, here's the star class we mentioned before, beginning on line 8. And the underscore init underscore, the dunderscore init method, to use the Python terminology, is a constructor. So if you come from the Java world, that's a constructor. It constructs a new star. And in doing so, we put some useful information that we got from the CSV file in there, like that HABF HVG is like a number, a reference number in the file. Convenient if you want to find that record in the file. The name is the name of the star, like Sirius or Procyon. Mag is magnitude, and that's how bright the star is, remembering, if you're an astronomical type, that larger numbers are dimmer stars and smaller numbers are brighter stars. You don't have to process that information in this program. Spectral is a spectral class of the star. It's a notation using letters and numbers. I don't fully understand it because I'm not an astronomer, but it has to do with the color and the nature of the star. And habit is a flag I found in the file that says whether or not it's habitable. Now stars aren't habitable, so I don't know what that means. Perhaps it means this star has planets in an orbit that potentially are habitable. I don't know. I just carried it along. And dist, we understand, that's distance. And the distance, that's how far away the star is from Earth, measured in this lovely unit called parsecs, which you can Google if you want to know more about it. Just know a parsec is a bunch of light years, and a light year is a bunch of miles. Okay, that's some damage to astronomy. That's what you got. All those things are arguments to the constructor, and they get stuffed in these member variables. So when you've read in something from the CSV file, you can construct a star out of it. Star has a convenience method called printme. I like to do a lot of those. It just makes it easy for debugging and checking your output to be able to tell the star to print itself, or tell any object to print itself. It's just handy. On line 23, is the definition of the class tree node. Now remember that tree node is the node structure that helps you build the tree. That's the things that are actually connected together by the left and right references in the tree, and they contain on line 27 a star. So all the star information you saw gets put into a tree node, and the tree node adds the crucial things on line 25 and line 26. It adds, I'll see if I can highlight those. It adds a left and right reference. That's the key to constructing a tree. Adding on the left, adding on the right to build a tree essentially in sort order by star name. I also made up a useful number potential. 28 says I made up a number for debugging in case you want to try to find a particular node in question. And the key, that's what we're going to use to figure out where this star, the tree node containing the star, where it goes in the tree. That's just the name of the star. Some of them you will have heard of, and some of them are you will not have heard of because they're pretty dim. The bright ones like Sirius and Procyon and Sol, our sun, you will definitely recognize, and some of the others, who knows. But they'll be compared when you're inserting, traversing a tree to insert, or traversing the tree to search. Those are what actually get compared to see if there's a match. There's a print me method that's just convenience to dump out for debugging purposes what the tree node looks like. And finally, on line 56, that's the actual tree. This is the collection. This is the binary tree that we build out of tree nodes, interconnected tree nodes, to contain the star data that we read from the file. It's got a, most important thing is the root on line 61. The name is unimportant, though you can name it just for debugging purposes. The root is there. The tree has a root, and the root is where you always start for searches and insertions, so it's very important. The orange text here in the triple quotes, that's called a doc string. Doc, as in document string, in Python, is just chopped out of the zybook. And this shows their pseudocode implementation of an insert. Now you can go find this in section 5.10 of the zybook, but just for convenience, I've inserted it here. It's a recursive insert. Comments on line 80 are probably irrelevant. Typical program has comments that are at worst misleading and at best useless. That's most programs end up with those. But in beginning on line 89, this is where there's some work for you to do. You have to code the insert method. The insert method takes a star object, wraps it in a tree node, and inserts it into the tree. There is also, there's some doc string here in orange that shows, well, that's the doc string up above, shows the insert. And the orange code beginning on 94, the doc string, that's what the recursive code looks like in pseudocode to print out the resulting tree. So that's what you will use to define, create, implement the pre-order print method on line 12 and 113. Pre-order just means going through the tree in alphabetical order, from the least node to the most node, where least and most are defined in terms of the ASCII value, the string value of the star name. So obviously, some of the trees we showed in the earlier video, some of the ones that have the Sol should end up being like the last tree printed. And I can't remember what one of the first nodes is. It's probably one with numbers. So there's an example there. And notice how short the recursive implementation is. Doesn't look like it does anything. And this is actually very characteristic of recursive programs. They're very short and very cryptic. Line 115 and down to line 136, this is a search algorithm It's a non-recursive search algorithm for searching through the tree to find a desired key. So you can implement that here as your search method or some other method to search through the tree for a given key. Right now, those methods just say pass. That just makes the code run but do nothing. Just a convenient placeholder. There are some utility functions. You don't need to do anything with the code from 150 to 184. That's the code I borrowed from the internet. It's actually a remarkable little program that prints those tree diagrams I showed in the earlier video, in the overview video. And it also is, guess what? It's recursive. But you need to use it, but you don't need to change it or add to it. Of course, main starts on 189. That's where execution starts in the program. It starts on line 192 by implementing a tree, an empty tree. So line 192 is actually it's like calling a constructor in Java. It's like saying tree, star tree gets new tree star catalog. But Python syntax just says, hey, just use the class name and I'll figure out that you want a constructor to be run. So after that, star tree now points to our tree. The code to open one of the star files and read it is on line 202 through basically 217. Now there are 3 files that you can use, and you should probably try to use all 3 because they get different results. Some of them have the same data. Well, we'll go through them. The HAB HYG shuffled, which is commented out currently, that's one ordering of 35 stars. Okay. HAB HYG short.csv, which is currently being used as an example, that's another ordering of the same stars. As you probably saw in the overview video, that gives you 2 different trees with 2 different roots, even though it's exactly the same data, because of the dependence of the insert method on the order of the data that comes in, because the tree is unbalanced. The last one is there should be I'll add another one, which is, it's interesting. I have a sorted, if you look on the left-hand side, I have a version called HAB HYG sorted. And that file is interesting because when you build a tree on it, the tree will look very odd indeed. And you'll begin to see one of the special cases where trees don't perform very well because the data are going to come in sort order. And of course, HAB HYG.csv with no suffix is a much larger file. I think it's 35,000 stars. It's useful to kind of test your program at scale. If you try to print the diagram for this, you better have a very small font and a very big screen because it's going to make a very dense tree. That's a lot of nodes, but it should work. It should be able, your program should be able to handle that many nodes. And it would be interesting to time some searches in that large tree. There we should start to see some differences. So the lines 212 through 217 are basically on 215. You see the star, we'll say constructor, that is a knit method being run to create a new star based on the row we just read from the CSV file. And then star tree.insert, that's the row that will actually insert the star into your tree once you code the insert method. Ops process is just a counter to make it easier to see if we got the right count or not. There's some timing there. You can have more sophisticated timing if you want. And then on line 255, we print out in pre-order. It's a pre-order traversal, to use the buzzwords. In other words, it's an in-order, alphabetical order printing of every node in the tree for the tree you construct. And on line 228, that's the code, again, my borrowed code from the internet, which actually draws the ASCII diagram showing the structure of the tree. So you want to run that too, because that also helps to let you know if you've got the tree structured correctly. Of course, the real test of whether or not your tree code works correctly is to search for various stars in the tree. So I've got a couple of examples there, searching for Procyon and Captain star. I don't even know what that is. It's probably pretty faint. And to see if they're found. Those stars should be found. Of course, you can also test with a star name that's not in there, like Fred, and see, make sure your search correctly says not found. Add a few more test cases there for stars that are in your tree, and then using the large file, that's just the HABHYG file, which is I think 30 some odd thousand stars. Try some searches in that and put timing around them, and let's see how long it takes. Should be entertaining. So there's quite a bit of freedom in the way you actually code these things. So as long as you get the correct results, I mean, that's fine. I don't care if you use recursion or don't use recursion. That's up to you. But there's not a lot to complete here, except that the insert method, for which you have the zybook pseudocode, is a bit tricky. And once you get insert, then the search is pretty easy, because the search, as I pointed out in the overview video, is just about like insert, except for what you do when you come to a null reference. So basically that's it. Please message me with questions and comments. Also use the discussion forum to get some suggestions and help from other students. I think I'm going to have you post the discussion board, and this is in the project description, some of the tree diagrams that are created by running your program on the short files, using different orderings of the data. And I think that we'll actually submit this code on an assignment, but I'm available to help out in any way at any time. So that's it for the walkthrough. I hope that helps. Again, I will talk to you going forward. Thanks.